Hi, everybody, and welcome to our talk. Many months ago, we had a realization that group testing can be used to increase the efficiency in COVID-19 testing. And we had another realization that contact tracing applications are increasingly available, and information gleaned from these applications can provide the group testing algorithms more information that can further improve their efficacy. We're going to tell you about our work in the following presentation. All the authors are going to be sharing in the presentation, and this is joint work by three institutions, IIT Bombay. The first author, Ritesh, comes from IIT Bombay as Ajit, the fourth author. Shu-Jie Cao comes from Shanghai Tech, and Chau-Wai Wong and I'm Dror Baron. We're from NC State University.
COVID-19 as of now is still a global challenge, and the testing is an important tool for help control the pandemic. The conventional testing procedure has 3 steps. The first step is to collect a sample from an individual's nose or mouth. The second step is to process the sample through a so-called RT-PCR procedure. The genetic material of the virus will be multiplied for many iterations so that their concentration or density will increase geometrically until the amplified viral load is eventually above a threshold for detection. By counting the number of amplification iterations, the initial viral load can be estimated, and the result is reported as positive. If there's no detectable virus after many amplification iterations, then the result is reported as negative. The RT-PCR process is a relatively resource-intensive procedure that can lead to false positives and false negatives due to a variety of technical or operational issues. Of course, we would like more efficient testing schemes for COVID-19 because an efficient scheme allows us to test more people, to test more frequently, and to test more accurately so as to help better control the pandemic. Group testing has been used to reduce the number of tests needed. The goal is to test a population of size n with fewer measurements of tests m, which is a number that is less than n. The initial idea was by Dorfman back in 1943 to test the individuals in groups. On the right-hand side, we're showing an example of testing light bulbs in groups of size 3. If they light up, then none of them is defective. If they don't light up, then at least one of them is defective. Each bulb will have to be tested individually. This 2-stage testing procedure is called adaptive group testing. It doubles the time to identify positive cases, which is not ideal for large-scale testing programs. Dorfman's approach also has some limitations. It has an implicit assumption of independently and identically distributed individuals. And it is also fragile to false positives and false negatives of the RT-PCR testing procedure.
Ever since the pandemic broke out, group testing algorithms have been applied for pooling for RT-PCR testing. We now review some progress in this area. The work by Hanel and Turner optimizes group sizes. In Zhu et al., a compressed sensing formulation with prevalence rates has been employed and using message passing style algorithms. In Ghosh et al., the noise in quantitative PCR has been modeled as a multiplicative noise model, and an end-to-end study of decoding in pooled quantitative PCR has been presented. This includes various aspects such as pooling matrix design, prevalence rate estimation, and a variety of different algorithms have been investigated. In Zhu et al., individual symptoms as well as family structure have been exploited in aiding the performance of the decoding algorithms. Independent work by Nikolopoulos et al. Exploited community structure with a focus on encoder design, but they did not consider the measurement or testing noise. We now review group testing using a compressed sensing approach. Let us consider a sparse vector of unknown health status of n different individuals. This is called as X. The health status values in a few entries are combined together to produce a large number of pools via a known sensing or pooling matrix A. This is a binary matrix where Aij is 1 if the jth sample contributes to the ith group, otherwise it is 0. A times X now gives us the ground truth health status in the m different pools. However, there is noise in the PCR process, which gives rise to a noisy vector Y of observed quantities giving noisy health status of m different pools or groups. The aim is now to estimate X given YA and the noise model. A variety of different decoding algorithms can be employed for this. This includes message passing or lasso. Other approaches are possible as well. All these approaches are single stage or non-adaptive, quite unlike the Dorfman procedure, which was two-stage and in which the output of the first stage acted as input to the second stage. The advantage of compressed sensing approaches for group testing is that side information can be very easily incorporated into the probability distribution of X. This side information can acquire the form of family structures or contact tracing information.
All right, so at this point, I'd like to describe our contributions. The main thing that we've done is to improve the efficiency of group testing by using side information or SI. We use two different types of side information. One is side information about family structure. Now, this is not only what people you live with, the household structure, the family structure per se. It's also, if you're in a study group together, that's also something that could easily, people could start infecting one another. If you play basketball or tennis or whatever, all of these are structures, family-like structures, where everybody's in close contact with one another, and thus it creates a certain sensitivity for infections. And you can see that if all you're doing is stay at home with your household members, then you're in one family, and then you'll have non-overlapping family structures, but you could also be in overlapping family structures. That's one type of SI. Another type of side information or SI that we considered is contact tracing data, where we considered who's in contact, the physical proximity between them, and the duration of the contact. Of course, the proximity and the duration have an impact on how likely it is that if you're infectious, you infected the other individual. We're plotting here two highlight plots. These highlight plots are for a data trace that we had. I'll describe soon some more details about it, with 1,000 people. On average, somewhat more than 4% or 40 people were infected at every point of time. And we took 150 measurements, all right? On the left and the right, the two panels are showing our results for binary noise and for multiplicative noise, respectively. And we achieved false negative and false positive rates of roughly 5%. On the left, you're showing results both for family and contact tracing for the binary noise. The family didn't work quite as well. The FNR and FPR were quite a bit higher. For contact tracing, the FNR and FPR were great. Regarding the panel to the right, we're showing 4 different algorithms. For each of these algorithms, we're showing results for 150, 300, and 375 measurements. Again, some of the methods performed very well, even using only 150 measurements. So another thing that I'd like to discuss here is that we didn't really have a public data set of who's infected, who's infectious, who they were in contact with, all that other stuff. So what we did instead, we looked at an SCIR type of model where part of the population is susceptible, others are infected. After a few days, you become infectious, and finally, you've recovered. Using this model, we generated, for a population of, again, 1,000 people, we generated traces using different parameters. On the panel to your right, you see alpha equals 1.76 and other parameters. This is infectiousness parameters, okay? And we got 4 different traces. The horizontal axis is the day number. The vertical axis is the number of people infected. You can see that the number of people infected is going up and down, but overall, we got 4 different traces of data that we simulated everything on.
Now, let's talk about the binary noise model. We have a binary health status vector of N individuals which is pulled into M groups by a sensing matrix A, and the intermediate vector W can be considered as the ground truth testing results. Since the PCR testing procedure is not 100% accurate, we assign a false positive of 0.1% and a false negative rate at 2% as used in Hanel and Thorner. We will estimate X using the generalized approximate message passing framework by Rangan, later applied to group testing by Zhu et al. The key is to design a proper denoiser in order to get good estimated results for X. The first denoiser is in the form of the conditional expectation of viral status of the ith individual conditioned on the pseudodata V, that is an intermediate quantity found in the GAM framework. And we design the family denoiser by using membership information to tune the probability distribution. Our second design is a contact tracing denoiser, in which we incorporate the 3 pieces of tracing information, that is who, how far, and how long contact was made, into the prior probability distribution of the X vector. We obtained the simulated results for our binary model. We show 4 plots at different sparsity levels, which means the ground truth positivity rates of the population. We can see here the contact tracing in the blue bars shows that it has much smaller false positive and false negative rates than using only the family structure as side information. If we look at any of the 4 panels here, we see the horizontal axis is the number of measurements. We see that when increasing the measurement rate from 50% to 30% to 37.5%, the group testing accuracy gradually improves, which is as expected. We can also see that by using contact tracing data as side information, the false positive and false negative rates are below 5%, except for the challenging cases where the true positivity rate is about 9%.
Let's now take a look at the multiplicative noise model. In this scenario, we allow the X vector to consist of non-negative real entries and regard W equal to AX as the true pooled viral load vector. Since the PCR process is noisy, the amplification of the viral load is modeled with multiplicative noise. We use group Lasso's variance as the decoding algorithm. To incorporate the family structure, since each individual belongs to a different family, we can construct an optimization problem that minimizes the distance between Y and AX while further penalizing the L2 norm of the subvectors of each family. The contact tracing scenario is slightly more complicated because the contact tracing data can result in overlapping groups. So we need to pre-process the data using freak detection and then design the cost function in a similar form. So let's now look at the results obtained using the multiplicative noise model. We can see the pink and blue bars in the figure that correspond to the family and contact tracing results respectively. These new results using family and contact tracing structure significantly outperform the decoding algorithms that don't use side information shown in red and black. Moreover, Model 2 allows us to estimate the viral loads of the infected individuals. Our experiments also show that both models M1 and M2 are robust to the inaccurate specification of contact tracing information, such as contact duration and physical proximity. To conclude, family structure and contact tracing can improve group testing efficiency. We have achieved almost 95% accuracy at 4% true infection rate, with the need for only 15% of tests required in a conventional testing scenario. To put things in perspective, with 4% positives, Dorfman pooling would require at least 40% tests. Yes, Dorfman improves over individual tests, and we provide a big additional improvement. Here are several future directions. We can try to design better group testing matrices by leveraging the insights from the coding community. We can also calibrate an exact number of pools to achieve the required performance. Finally, a third direction is to explicitly model PCR noise to potentially further improve the testing efficiency. Thank you.